Chapter 4, Force and Motion. Force and motion covers Newton's laws, some particular forces, the gravitational force, the normal force, friction, tension, free body diagram. You can find them in a timeline. Newton's laws. What causes an acceleration? The change in velocity must be due to an interaction between the body and something in its surroundings. An interaction that causes an acceleration of a body is called force, which is, loosely speaking, a push or a pull. The relationship between a force and the acceleration it causes was first understood by Isaac Newton, and the study of that relationship, as Newton presented it, is called Newtonian mechanics. Great scientist, Newton, everybody knows. Newtonian mechanics does not apply to all situations. If the speeds of the interacting bodies are an appreciable fraction of the speed of the light, we must replace Newtonian mechanics with Einstein's special theory of relativity. If the interacting bodies are on the scale of atomic structure, for example, they might be electrons within an atom, we must replace Newtonian mechanics with quantum mechanics. Physicists now view Newtonian mechanics as a special case of these two more comprehensive theories. Still, it is a very important special case because it applies to the motion of objects ranging in size from the very small, almost on the scale of atomic structure, to astronomical objects such as galaxies and the clusters of galaxies. Newton's first law. Newton's first law. If no force acts on the body, then the body's velocity cannot change. That is, the body cannot accelerate. You do not need a force to keep a body moving with constant velocity. Soccer athletes are those people who apply the Newton's first law most skilled. Inertial reference frames. Newton's first law is not true in all reference frames, but we can always find reference frames in which it and the rest of the Newtonian mechanics is true. Such frames are called inertial reference frames, or simply inertial frames. An inertial reference frame is the one in which Newton's law holds. Vice versa. If Newton's laws hold, then this frame is an inertial frame. We usually assume that the Earth's ground is an inertial frame, and that measurement of forces and accelerations are made from it when Earth's rotation can be neglected. See, only we neglect the Earth's rotation effect, then we can treat it, the Earth's ground is an inertial frame. Don't forget this one. It's just, strictly speaking, the Earth's ground is a non-inertial frame because the Earth is rotating.
If a glider is at rest on a track and the track is shifted from side to side, the glider will move with the track. Air is now forced through holes in the side of the track so that the glider is supported on a cushion of air. What will happen now if we shift the track from side to side with the air turned on? The glider is now motionless. If we give the stationary glider a single push, it moves at a constant speed after the force is gone. We'll try to remove the tablecloth from under these dishes without making a mess. How? By yanking the cloth out very fast. Pull slowly and the table setting moves. This will have to be done much more quickly. A metal tube wrapped inside the loose edge of the cloth provides a firm grip for a fast pull. When the cloth is yanked out fast, the dishes barely move.
Could you remove this pizza pan from under these eggs without touching or breaking the eggs? If the eggs could be made to drop straight down, they would land in these water-filled beakers and would survive intact. By striking the pizza pan hard with this broom handle, the pan will fly out, allowing the eggs to drop straight down into the beakers. Let's try it. The pizza pan shot out so fast that the eggs barely moved. Let's watch again in slow motion.
A ball given a push inside an aluminum ring rolls around inside the ring. When it reaches this gap, which path will the ball follow? Will it follow this path, or this path? The ball follows a straight line in the same direction it was moving at the point of escape. Its path is tangent to the circle at that point.
Newton's second law. First, a force causes the acceleration of a body. We now wish to define the unit of force carefully in terms of the acceleration that it gives to a standard reference body. As a standard body, we use, or rather we imagine that we use, the standard kilogram. This body has been assigned exactly a mass of 1.0 kilogram. We put the standard body on the horizontal frictionless table and pull the body to the right so that by try and error, it eventually experiences a measured acceleration of 1 meter per second per second. We then declare, as a matter of definition, that the force we are exerting on the standard body has a magnitude of 1 Newton, abbreviated capital N.
We will use a glider floating on a cushion of air and a light spring to demonstrate how a constant force from a spring can accelerate the glider. The spring is attached to the end of the glider, and a marker stick is attached to the top of the glider to indicate the extension of the spring. When the spring is pulled out, it pulls on the glider with a constant force. The force from the spring accelerates the glider. Here is the same acceleration repeated, with dots on the screen recording the position of the glider every half second.
In general, if our standard body of 1 kilogram mass has an acceleration a, we know that force F must be acting on it, and that the magnitude of the force in newtons is equal to the magnitude of the acceleration in meters per second per second. A force is measured by acceleration it produces. But acceleration is a vector quantity with both magnitude and direction. Is force also a vector quantity? The answer is yes. Forces are indeed vector quantities. They have magnitudes and directions, and they combine according to the vector rules.
This cart on an incline is acted on by three forces: a downward gravitational force, a force along the direction of the incline supplied by this weight and string, and a force perpendicular to the incline provided by the incline itself. A mass hanging over this pulley will provide a force equal to the force from the incline. At this point, do we need the incline? The incline is no longer needed. It can be removed and the cart will stay in place.
The strings tied to this ring exert forces on the ring. Masses hanging from the ends of the strings provide the actual force. A 500-gram mass on this string, an 866-gram mass on this string, and a 1,000-gram mass on this string. If we pull the ring away from the center, it returns to its original position. The ring is in stable equilibrium. These vector arrows represent the force exerted by this string and the components of that force in the horizontal and vertical directions. Here is a similar analysis for the second string. The horizontal components of the two forces are already in balance. The third weight must equal the sum of the two vertical components, or 9.8 newtons.
Henceforth, we shall use bold-faced letters, most often capital F, bold font, to represent forces. And we shall use the symbol sigma F for the vector sum of several forces, which we call the resultant force or the net force. As with other vectors, a force or a net force can have components along coordinate axes. Finally, we know that Newton's first law is no force on a body, but also when the net force is equal to zero. So the Newton's first law can be rewritten as if no net force acting on the body, sigma F equal to sigma net equal to zero, then the body's velocity cannot change. That is, the body cannot accelerate. Mass. Everyday experience tells us that a given force produces different magnitudes of acceleration for different bodies. We can explain how to measure mass by imagining a series of experiments. In the first experiments, we exert a force on our standard body, whose mass m is defined to be 1.0 kilogram. Suppose that the standard body accelerates at 1.0 meter per second. We can then say the force on that body is 1.0 Newton. We next apply that same force. We will need to some way to be certain that it is the same force to a second body X, whose mass mx is not known. Let us then make the following conjecture. The ratio of the masses of the two bodies is equal to the inverse of the ratio of their accelerations when the same force is applied on both. So mx over m equal to a over ax. Same force applied. Okay, this is conjectures. Our conjecture will be useful, of course, only if it is continue to hold when we change the applied forces and the standard body M to other value. This one ought to be true because in this measurement condition, we have two variables. One is the force. Before we use the standard force, 1 Newton. Now we change to other force. See whether this is true. Or we change the standard. Instead of 1 kilogram, we use the other number. And we find we change the standard, we change the force, and we find this AX is the same. MX is the same. MX is the same. So many experiments yield similar result. That means MX is the same thing. Indicate that our conjectures provide a consistent and reliable means of assigning a mass to any given body. So we can assign a mass to anybody, okay, just by this experiment. Our measurement experiment indicate that mass is an intrinsic characteristic of a body. That is, a characteristic that automatically comes with the existence of the body. They also indicate that mass is a scalar quantity, no direction, only magnitude. The mass of a body is the characteristic that relates a force on the body to the resulting acceleration. The net force F net on the body is the vector sum of all the external force. F net equal to sigma F external. Newton's second law. The net force on the body is equal to the product of the body's mass and the acceleration of the body. F net or sigma F equal to ma. We see A is a vector, so we can write it in vector form: AXI plus AYJ plus ACK. Remember, all these forces must be on that body, okay? If F is not on that body, it's nothing to do with situation. 2. Vector sum. This is a vector sum. It's not algebraic sum, vector sum.
If a string hanging over a pulley is loaded with a small weight, it provides a force which can accelerate a glider floating on a cushion of air. Here is the same acceleration, with the position of the glider marked by dots at half-second intervals. If the force is doubled by doubling the hanging mass, how will that affect the acceleration of the glider? The dots are more widely spaced, so the acceleration has increased. If the same hanging weight is now used, but the glider's mass is doubled, how will the acceleration change?
With double force, double mass, see what happens. Acceleration should be the same.
Here is the new acceleration. Here are all three accelerations and the force and mass data for each.
They're the same.
This device is known as an Atwood's machine. Two equal masses hang on either side of a string passing over a pulley. Since the masses are equal, there is no net force to accelerate the masses, and they are in equilibrium in any position. A small rider is now added to one of the large masses, and the system begins to move. How could we best describe this type of motion? Since there is a constant unbalanced force on the system, it is accelerated. The traces left behind each half second in this segment show the acceleration. If the mass now passes through this ring so that the rider is picked off, how will the motion of the masses be affected? The masses now move with the constant velocity. Here is the same sequence repeated with 2 riders added to the large mass.
When this large rock is struck with a hammer, it barely moves. Why does this rock behave so differently? The first rock is real and very massive. The force of the blow barely accelerates it at all. The second rock is made of low-mass foam rubber. The same blow from the hammer on this rock causes a very high acceleration.
Sigma F equals F net equal ma. Newton's second law. We know sigma F is a vector, so it has 3 components. F net, the same thing. They have F net xi, F net yj, F net k, and A is a vector. So ijk is a unit vector along 3 axes. They had nothing to do with relationship. So we compare the coefficient in front of I, j, and k. We get sigma fx equal to max, sigma fy equal to may, or sigma mfz in front of k equal to mack, or f net x equal to max, f net y equal to may, f net z equal to mz. These equations relate the 3 components of the net force acting on the body to the 3 components of the acceleration of that body. 3 components are independent with each other. Well, look at this one. The acceleration components along a given axis is caused only by the sum of the forces component along the same axis, as not by force component along some other axis. Look at this. AX is only related to FX, nothing to do with FY or FC. And FC is only related to AAC, nothing to do with AY and AX. You should know that Newton's second law encloses the formal statement of Newton's first law as a special case. For metric system unit, 1 Newton equal to 1 MA, 1 kilogram meter per second per second. Unit in Newton's second law. Unit. Force, we use a Newton. Mass, we use kilogram. Okay. Acceleration, meter per second per second. Okay. And 1 Newton equal to 1 kilogram multiplied by 1 meter per square per square. Newton's third law. When 2 bodies interact, the forces on the bodies from each other are always equal in magnitude and object interaction. Relax. A book is lying on a crate C. Okay. We have 2 forces. One is the force CB, force acting on the crate by book B. Another one is FBC, the force acting on book by crate. They are equal and opposite, but they never cancel out. Why? Because they acting on different objects, so they never cancel out. FBC equal to minus FCB, the vector, direction, magnitude. Forces come in pairs, also pairs. Commonly, one of these factors, it doesn't matter which, is called the action force. The other member of the pair is then called the reaction force. They never cancel with each other. Now we look at this cantilever at rest on the table. It exerts two forces, okay? It's at rest, so the sigma F equal to 0. You have two forces acting on it. At some points, some students say, hey, you see, this pair cancel out. These forces is cancel out. They are equal in magnitude and opposite direction, acting on the same cantilever. Let's look at what they have pairs. This one, acting on the cantilever by Earth, is paired with acting on the Earth by cantilever. And this force acting on the cantilever by table is paired with this force acting on the table by cantilever. Okay, they are different pairs, but they cancel out because they acting on the same object. In this case, cantilever.
If one object pushes on a second object, the second object accelerates. But what about the object doing the pushing? Does it also accelerate? We will use these gliders floating on an air track to find out. This spring bumper will provide the force from the first cart on the second. If we tie the carts together with the string so that the first cart is pushing on the second, then burn the string, what will happen to the first cart? Both carts accelerate. When one object pushes another, the second object pushes back. For every action, there is an equal and opposite reaction.
We'll use this radio-controlled car and a board on rollers to demonstrate action and reaction forces. The car and board are both initially at rest. When we start the car moving to the left, the board moves to the right. The car exerts a force on the board, and the board exerts an equal and opposite force on the car. This animation shows the forces that act between the car and the board.
This small cart has a motorized fan mounted on top. When we turn on the fan, the cart moves off to the side. If we put a sail on the cart and turn on the fan, which direction will the cart move? The cart doesn't move at all. If we blow on the cart with a fan, which is not attached to the cart moves in the direction of the airflow. This animation shows the force acting on the cart without the sail. Here are the forces acting on the cart when the sail is in place. And this is the force which acts on the cart when the external fan is used.
Some particular forces. The gravitational force Fg. A gravitational force Fg on a body is a pull that is directed towards a second body. We usually consider situation in which the second body is Earth, and the force that pulls on it directly toward the center of Earth, that is, directly down towards the ground. Fg equal to mg, as g is always towards the center of Earth. We should assume that the ground is an inertial frame. So Fg equal to mg. Okay. Where g represents the free fall acceleration vector. Now, you have the choice. Take the y direction, positive is upward, and g is always downward. So in this case, rewrite it, equation, rewrite minus j fg. Okay, we have direction here, minus g, because it go down. This fg is mg minus mg. Okay. If you like to choose reference y positive downward, then g is downward, the positive number. So first two term the same, fg equal to mg. But in this case, we choose the reference direction, we can write it g is a positive number, so it's equal to fj is mg, and fg is mg. So this one is minus mg, this one is mg. Which one is right? Okay, they can both right or they can both wrong. Depends on how you match them. Okay, this formula for this reference, this formula for this reference. Weight. The force exerted by Earth is called the weight W of a body. This force is directly toward the center of Earth. The force is due to an attraction called a gravitational attraction between the two bodies. The weight W of a body is primarily equal to the magnitude Fg of the gravitational force on the body. Notice that primarily. We will talk about this in detail later. Now compare the weight and mass. Weight is a vector, okay? It's not constant. At different places you take up objective weight, it's different, okay? And it's not intrinsic property of the body because it changes, okay? And mass is a scalar. It's constant. It's intrinsic of the body. Everywhere mass is the same, but weight are different. Unit, the weight is called a Newton, the force. Mass is a kilogram, mass, okay? How do you measure it? Okay, this weight we use the spring scale. And mass, you must compare, use the balance, compare with other things, okay? Now, we use the spring balance to measure it, okay? You measure this one in different places, you get different answer, okay? And mass, we use the balance to compare with the standard mass. So you measure it everywhere in the world, they get the same answer. Next, normal force. When a body is pressed against surface, the surface, even a seemingly rigid surface, deform and pushes on the body with a normal force N that is perpendicular to the surface. It's called a normal force. We write the free body diagram on this body, two forces acting on it. One is gravitational force, one is normal force. And these two forces equal in magnitude, opposite in direction. So this body is balanced. Sigma F equal to 0. It's at rest. Also, N minus mg. Okay, MAY equal to 0. So N equal to mg. Okay? F equal to mg, N equal to mg, okay? Remember, the normal force equal to mg is only in this case. We never define the mu, okay? Anyway, okay? Friction. If we slide or attempt to slide the body over a surface, the motion is resisted by a bonding between the body and the surface. We discuss this more in the next chapter. The resistance is considered to be a single force, F, called frictional force or simply friction. This force is directed along the surface, opposite the direction of the intended motion. Sometimes, to simplify a situation, friction is assumed to be negligible. and the surface is said to be frictionless, no friction. Tension. When a cord or the rope, cable, or other such thing object is attached to a body, this one, a body, and pulled out, the cord is said to be under tension. This was under tension. It pulls on the body with the force T, whose direction is always from the body. This T is all leaving the body. Okay, those directions are always from the body and along the cord at the point attachment. The cord is massless in our study. Then you see you have a pulley. This tension is equal to this tension. This tension equal to this tension because they are frictionless, okay, and they're light. If they are not frictionless, they are not light, that would be different. Okay. Now, if a cord is at rest, then we see that tension is uniform. Now, let's look at a section of it, mass M. We have two tension. On the right is T2, on the left T1. Over here, we have so T1 minus T2 equal to M8. If this is light, that means massless. This is 0 compared to this one. In this case, T1 equal to T2. 8. Or it at rest, A is 0. So this is 0. Okay. So that one, the tension in a rope is uniformly equal to one thing. Okay. Free body diagram. Free body diagram. To solve problems with Newton's second law, we often draw a free body diagram. 1. Representing the body by a dot. 2. Each external force, or the net force sigma F, that acts on the body by a vector with its tail on the dot. Instead of the dot, we can sketch the body. 3. A set of coordinates axes is included. 4. Sometimes a vector presenting the acceleration of the body is also included. Example. In Figure A, to see, one or two forces acting on a puck that moves over frictionless ice and along an x-axis in one-dimensional motion. This is F1, F2, F1, F3, F2. Force 1 and 2 are directed along the x-axis and have magnitude F1 4.0 Newton, F2 2.0 Newton. Force 3 is directed at angle theta 30 degrees and has magnitude 1.0 Newton. In each situation, what is the acceleration of the puck? Now, this is given. Okay, this is very simple. This is the dot. Okay, we have a force tail at this dot. Okay, so we have F1 equal to max. We put F1, we put M, we get AX. Second, we have two forces. So dot, we have two forces. This is positive direction. So F1 minus F2 equal to MAX. We have F1 and M, we get AX in this case. Okay. Third one, along the X direction, we have F3 cosine theta minus F2. This is a diagram. F3 cosine theta, F3x minus 3 FA. So we find AX is minus. That means the direction is this direction, acceleration. Okay. Sample. In the overhead view of a figure A, we look at this one. A 2.0 kilograms cookie tin is accelerated at 3.0 meter per second in a direction shown by 8 this direction, 50 degrees to the x direction. Okay. The acceleration is caused by 3 horizontal forces, only 2 of which are sure. You have 3 forces. F1, this one, 30 degrees. F2, along y direction. Okay. F1 of magnitude 10 Newton and F2 of magnitude 12 Newton. What is the third force, F3? A unit vector notation and as a magnitude and an angle. We know that the physics is F1 plus F2, F3, sigma F equal to ma. We know A. We know F1, F2. We want to have F3. So it's very easy. This is a vector equation. F3 equal to ma minus F1 minus F2. Or we can look at it as ma plus minus F1 plus minus F2. Now we drop it. Okay. This is ma. Okay, like 50 degrees. Plus minus F1, this is F1. Minus F1 go this direction. Plus minus F1. Plus minus F2. This is F2 plus minus F2. And we get this one's F3. Right? Yeah. So then look at this F1. This is minus F1. This is F2. This is minus F2. We put together, you get this. This is F3, exactly the same way. Okay? Okay. What do we do? This coordinate is F1 plus F2 plus F3 equal to M8. In this way, this is exactly the same thing. All right, we'll do it. We divide into the X component and Y component. For this one, F3X equal to MAX equal to F1X minus F2X. That's it. Okay. We put the details. Let's see. This is a MAX equal to MAX A cosine 50 degrees minus F2. F2 is minus 150. Okay, the angle. Okay, and F2 is 90 degrees. Let me look at this one. Okay, this one is 30 degrees. So this is minus 150 degrees. This is F1. Okay. Okay. This will put everything inside. We're going to 12.5 Newton. That's F3X. And the F3Y equal to everything get Y equal to 3Y. MAX, MAY minus F1Y minus F2Y. Okay? And F2Y. So we put those in everything. Okay? We get F3Y minus 10.4 Newton. Put them together. F3 equal to F3xi plus F3yj. And we take the two significant figures. So this x is 13. This is minus 10. Okay. Once you know two components, we can get F3 equals square root F3x squared plus X3y square root 16 Newton. And the angle is tangent angle is F3y over F3x. So for theta is minus 40. These are very easy ones. Applying Newton's laws. The rest of this chapter consists of sample problems. You should pore over them, learning not just their particular answers, but instead the procedures for attacking a problem. Especially important is knowing how to translate a sketch of a situation into a free body diagram with appropriate axes, so that Newton's law can be applied. Sample. Figure shows a block S, the sliding blocks, whose mass m 3.3 kilogram. The block is free to move along a horizontal frictionless surface, such as air table. This first block is connected by a cord that wraps over a frictionless pulley to a second block, H, the hanging block, with mass m 2.1 kilogram. The cord and the pulley have negligible masses. Compared to the blocks, they are massless. The hanging block H falls as the sliding blocks S accelerate to the right. Find A, the acceleration of the sliding blocks. B, the acceleration of the hanging blocks. 3, the tension in the core. Now, answering. Blocks can be treated as a particle. Means every small part of the block moves in exactly the same way. 2, the only function of the pulley is to change the direction of the core here, massless and frictionless. Now, let's write that free body diagram for block S. How many forces acting on it? We have the normal force from the tape. We have gravitational force from the Earth. And then we have the tension from the core. And the 3 forces, it moves to the right with acceleration. So we write equation. Okay? What equation? Horizontally, T equal to ma. Second, you see this. N minus gravitational force equal to mg equal to 0 because it does not move along this direction. Acceleration is 0. Okay, we have 2 equations. Now let's look at the free body diagram for the hanging blocks. You have a T upwards, gravitational downward, and acceleration, right? So this acceleration should be positive, should downward, because the sliding blocks goes to the right, it goes down, right? And we write it equal to F mg minus T equal to ma. Okay, this is equation, all right? This T and this A are shared with the previous equation. That's the interaction between them, okay? Now, someone will say, I don't want this one. I want to see T minus mg equal to ma. Can I write this one? Of course, this is for a single equation, it's okay. But in that case, you assume the A is upward, is opposite to this A, and is not conflict with the previous assumption. The previous assumption is if the sliding box go to the right, this one go to down. So you have to write this one. Now, formally, what we do is, look at this one. Okay, we have a frame, this X, this is Y. What do? We do is mg sigma F equal to ma. And then we write this one. Mg for this one is minus 1, because this is up. Minus mg plus T equal to minus ma. This is, we write, this is the one. Okay, this is formal, okay? All right, so we have 2 equations. This is 2 equations. 2 unknown. It's very simple to get the answer. I'm not going to do it, okay? A, got an A, and we got a T. I just discussing the result, okay? The discussion. You see, mg is 20 Newton. This is the one. T is 13 Newton. So this one is going down. This is a reasonable answer, okay? Suppose G equal to 0. G equal to 0, A is 0, okay? A is 0, T is 0. That's right. Without gravitational, you don't have a weight. You don't have a force to go. That's right. 3. If M equal to 0, this is 0. You see, this acceleration must be G, free fall, okay? The A equal to G and the T equal to 0 because it's free. 4. This is to infinity, or this is nothing. So we go free, A equal to G and the T equal to ma, okay? Sample. In figure A, a block B, of mass 15 kilogram, hangs by a cord from a nut K of mass mk, which hangs from ceiling by a means of two other cords. The cords have negligible mass, and the magnitude of the gravitational force on the nut is negligible compared to the gravitational force on the block. What are the tension in the three cords? 1, 2, 3. This is compared to this is nothing, okay? 1, 2, 3. They are in equilibrium, no acceleration. Okay? We could this one. We write the free body diagram. You have two. One is gravitational force, one is T3. So easily, T3 minus Fg equals 0. It does not move, no acceleration. So T3 to mg. Okay. Second, we could this one. Okay. At this point, we have three forces. It is balanced. It is balanced. Okay. Okay. So we write free body diagram T3. We know that's one mg. T1 and T2. This angle knows. I don't know the force. Okay. So it is balanced. That means sigma f equal to 0. Sigma f equal to 0 means the component along x direction is 0. Along y direction is 0. So we have two equations. Okay. Sigma f equal to T1 plus T2 plus T3 equal to 0. We write it down. This A is 0. We write it down. Okay. Sigma fx, x, this is nothing. This is minus T1 cosine 28 plus T2 sine 47 equal to 0. This one is C. Sigma fy equal to 0. This is T1 sine 28 degree plus T2 sine 47 degree minus T3 equal to 0. Okay, you see we have a 1, 2, 3 block equation. We have three unknown, T1, T2, T3. That's that. Okay, I get the answer. Okay, very quickly. Example. In figure 8, a cord holds a block mass m 15 kilogram on a frictionless plane that is inclined at an angle theta 27 degree. Question A. What are the magnitude of the force T on the block from the core and the normal force N on the block from the plane? Two things. Okay. Now, let's write the free body diagram. This is mg, this is a T, this is normal force. We have three forces. Okay, it does not move. That means sigma f equal to 0. All right. Now we take reference frame x along the inclined surface up, y perpendicular to the surface. Then we have this gravitational force, tension, normal force. Okay. And this angle is equal to the theta. Okay. Because this perpendicular this perpendicular this. So this theta equal to this theta. Right. Now we write the equation. Okay. Write the equation. We divided the gravitational force into two components. Fgx, this is F sine theta. Fgy is Fg cosine theta. And we rewrite the equation. Sigma f equal to T plus N plus mg equal to 0. In detail, along x, along y. So Fx equal to Tx. T is along x. N is 0. This is angle 0. Okay, this is 90 degree 0. Theta is 0. Okay. Mg, okay, this is mg. This is mg. Sine theta is along this negative. Okay. So we get it. This one equation, and sigma fy equal to 0. Fy, this one is nothing to do with t. N minus mg cosine theta equal to n minus cosine 27 degree. We have two unknown, t, n. We have two equations. So very simple, we get the answer, t and n. Question B. Now we cut the cord. As the block then slide down the inclined plane, does it accelerate? If so, what is its acceleration? When we cut down, we see how many forces acting on it. This is gravitational force and a normal force. So only two forces acting on it. We see they have component along the inclined surface. Okay. So this is x up. So we had sigma fx equal to 0 minus mg sine theta. This does not have components, so equal to max. So we get max equal to minus g sine theta. Okay. And you find this one is nothing to do with m. Any mass will get the same acceleration. Sample. In figure A, a constant horizontal FAP of magnitude 20 Newton is applied to block A of mass MA 4.0 kilogram. This is 4.0 kilogram. F is 20 Newton, which pushes again block B of mass 6.0 kilogram. The block slides over frictionless surface, no friction, along an axis. This is x direction. Question A, what is the acceleration of the blocks? Question B, what is the force FBA on block B from block A push B? Now, we look at this one, we have different way to do it. First, we look at this A. The A move, A was exerted two forces. This is force A applied and force A by block B. Okay. Then we see this one minus this one equal to MAA. And we look at the B. B was exerted by block A with the FBA. FBA equal to FAB. They are a pair of Newton third law. So we have FBA. FBA is equal to MBA. We combine these two equations, we get FAP equal to MAA. Okay. And this A is FP divided by MA and MB. I get the answer. Or you can, very simple, you can consider this is 2 is in 1. So the mass is MH and B, F. So this is A equal to F, MH and B. Second B, what the force here? All right, that is very easy, okay, because you know the acceleration, okay. You know this one, we can find FAB or FBA, right? First. This is another way to do it, okay. We take this as 1, so we get a FAP equal to MA plus MBA, and we get an A instantly. Then, you know it's A, it's M, so FBA equal to MBA. This one looks like easier than the previous one, okay. Next lecture, Chapter 5, Friction. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They help a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.